Molecular shape and polarity are important properties of molecules. They affect both how a molecule will react chemically as well as its physical properties such as melting point and boiling point and viscosity and so forth. We can use VSEPR to help us understand the molecular shape of a molecule, and electronegativity in combination with molecular shape can tell us about the polarity of the molecule, or help us to predict the polarity of a molecule. Recall that electronegativity is the ability of an atom in a molecule to attract the electrons in a bond towards itself. So this is really about a competition for electrons in a bond between two atoms. If we look at this HF atom, the fluorine and the hydrogen have electronegativity values which we can estimate just based on the trend in the periodic table. Remember that electronegativity increases up and to the right. Hydrogen is over here, fluorine is over here. Fluorine is, in fact, the most electronegative element on the periodic table, and so it has a much higher electronegativity than does hydrogen. So if we look at the electrons that are shared in the bond between these two atoms, we find that fluorine will share a little unequally. It will pull more of that electron density towards itself, producing a slight negative charge on the side of the molecule with the fluorine, and a slight positive charge on the side with hydrogen, as shown here by the blue and the red intensities of the color. That produces a dipole moment. When you have a separation of charge, negative and positive charge like this, we get a dipole moment on the molecule. In fact, HF will behave like a little magnet. So if I have several HF molecules, each with their own dipole moments, right, they'll be attracted based on their negative and positive ends. The strength of the dipole moment is going to increase with increasing differences in electronegativity between the bonded atoms. So if we look at these four examples, HH, HBr, HCl, and HF, well, hydrogen has an electronegativity of about 2.2. Bromine 2.96, chlorine 3.16, and fluorine 3.98. And these electronegativity values you can look up in your text or online, for instance at ptable.com. Now notice that the trend is increasing electronegativity up from bromine, chlorine to fluorine. This produces a greater difference in electronegativity between fluorine and hydrogen than between bromine and hydrogen. And of course, two hydrogens bonded together will have no dipole moment because they have the exact same electronegativity. But each of the other molecules will have slight dipole moments, as shown here, based on the difference in electronegativity between those atoms and hydrogen. Bromine, for instance, will pull electrons towards itself slightly more than hydrogen can compete with it, and that leads to a small dipole. However, the dipole moment in HCl will be slightly bigger, and in HF even larger, and I'm representing that with the larger arrows, because the difference in electronegativity between hydrogen and those other elements increases. So you can think of it as in this case, sort of no dipole moment, no magnet, right? A weak magnet, slightly stronger magnet, the strongest magnet in terms of the strength of the dipole moment. But what about molecules with multiple bonds? How do we determine the polarity for these? It becomes a little more complicated because you can have multiple bonds, right, with dipole moments. So take these two for instance, CO2, carbon dioxide, which is linear, and water, which is bent. Now, in this CO2 molecule, oxygen is much more electronegative than carbon, right? It's further to the right on the periodic table. So I should have a dipole moment, right, towards the carbon on both bonds, right? The oxygens are pulling electron density in those bonds away from the carbon. But in this case, they're on opposite sides from each other, and therefore they cancel each other out, and there ends up being no net dipole moment. So when I have these polar bonds symmetrically arranged around the central atom, they will tend to cancel and then leave no net dipole moment for the molecule. So CO2 is nonpolar. However, water is bent, and oxygen, being more electronegative than hydrogen, leads to dipole moments on these bonds. The net dipole moment for the molecule will be in the direction of both arrows. So you can think of them as vectors which add in the direction shown here, leading to a negative side and a positive side for the whole molecule. In these very symmetric molecules, even though they all have polar bonds between the central atom and the very electronegative fluorine atoms, the net dipole moment for these structures is 0, and therefore these are all nonpolar. So when you see very symmetrical molecules with these geometries as shown, with all the same atoms around the periphery, right, the terminal atoms are all the same atom type, then you're going to have a nonpolar molecule. You can think of that because, for instance, on all these polar bonds between the sulfur and the fluorine, right, the dipole moments on each side of the sulfur cancel each other, leading to no net dipole moment for the molecule. And the same with this BF3, the dipole moments on each of these bonds arranged symmetrically around boron end up canceling. However, if we change just one atom so that we lose some of the symmetry, now the fluorines are not all balanced. So we have hydrogen and boron have essentially no dipole moment on that bond because boron and hydrogen are essentially the same electronegativity. But we do have strong dipole moments on the boron-fluorine bonds, and that leads to a net dipole moment in the direction shown. In addition, if we change a fluorine in the PF5 to chlorine, now the chlorine is not as electronegative as fluorine, and so the PCl bond has a weaker dipole than the PF bond, and therefore you'll have a net dipole moment in the direction towards the chlorine. So we have a positive end of the molecule and a negative end of the molecule. You can think of this as the fluorine is more electronegative and essentially outcompetes chlorine for the electrons in those bonds. And it pulls more of the electrons towards itself, leading to a negative charge up on the fluorine end and a positive charge on the opposite sides where the chlorine is.